All right, let's try this again. The second time I've tried to record this video. So I hope that this one goes better. So we're going to look at exploration 1-4A, and it's on definite integrals, which we've talked about already. So this is just kind of to reiterate what we've talked about. We're going to look at trapezoids again, and then what the area under a curve gives us in context of a problem. Okay, what does a definite integral give us in context of a problem? So let's take a look at our problem. We have a rocket problem. Elevator, Darth's daughter, is driving in her rocket ship. At time t equals 0 minutes, she fires her rocket engine. The ship speeds up for a while, then slows down as Alderaan's gravity takes its effect. The graph of her velocity, v of t, in miles per minute is shown below. So here's our graph of v of t. We've got time along the bottom. That's in minutes, right? And velocity along the side, that's in miles per minute. I always like to keep track of those things, okay? And the first question is, what mathematical concept would you use to estimate the distance Ella goes between t equals 0 and t equals 8? Okay, so let's find, all right, here's time 0. And let's see, 5, looks like 6, 7. Looks like this would be 8. Okay, and I want to know what mathematical concept could we use to estimate the distance if I am giving velocity. Okay, so we could use a definite integral, which actually would give us the exact distance Ella went. And so if we want to approximate it, we really just find the area, or find or estimate the area under the curve, right? Between the curve and the x-axis. Estimate the area under the curve, all right, which will eventually, we will turn that into a definite integral if we want to get the exact, right? But if we don't have an equation, if we don't have a function, then the best we can do is estimate. Okay, by estimating the area under the curve. And one way that we've done that is by counting blocks, right? And so number 2 actually says estimate the distance in problem 1 that we were just talking about by counting the squares. Okay, so I definitely encourage you to pause the video and actually take the time to count the blocks. Remember, if it's not a whole block, you're going to have to estimate whether it's a half a block or 0.4 of a block or something like that, okay? And then see what you come up with, okay? So pause the video. All right, here's what I came up with. I came up with roughly, again, I'm estimating, 60.8 squares, okay? But you have to understand that that is not necessarily her distance, okay? That's just how many blocks there are, okay? I have to figure out how much is each block worth. Like, is it literally a distance of 1 mile, or is it more than that? Okay, well, let's see. The time unit, you can tell, it looks like it's broken up. All right, if this is 5, then this is 1. So the time unit is 1 unit wide. But then how tall is each block? All right, well, if I count up to 4 places and get to 100, then 1 block must be 25, okay? So the area of 1 block, is literally 25 miles per minute times 1 minute. Length times width would give me 25 miles per square, right? 25 miles each, okay? So 60.8 squares times 25 miles each will give me, and remember we're approximating, the 60.8 was approximation, 1,520 miles. Okay, now number 3 says Ella figures that her velocity is given by this velocity function, this cubic function. So we're going to plot this on our calculator, and we want to see if this graph confirms or refutes what Ella what Ella is thinking, okay? And then let's talk about how we're going to arrive at that conclusion. So what I'm going to do is I am going to pull up my calculator here. And how am I going to graph this? All right, well, I'm going to go to y equals. Now, I can't type in a t. I'm going to have to use an x. So I'm going to do x raised to the third. All right, where's my function? Minus 21x squared. I'm just literally doing the function there at the bottom of the screen. Plus 100t, or 100x, plus 110. Now, if I hit graph right now, it's definitely not going to look like that because the standard window is, I'll even show you, is a 10 by 10. Okay? So we're going to change the window to match the window here that's provided. So it looks like I'm going from 0 to, what, 11? So 0 to 11 for the x-axis, and then for the y-axis, it looks like I go from 0 to, let's see, 225, 50, 275, 0 to 75. Okay, and then I'm just going to hit graph. All right, now, of course, this graph goes a little bit further than the one on the paper because the one on the paper stops a little past 8. All right, but we went all the way to 11 just to match up the windows. All right, and I know the scale is a little different. Let me see, I wonder if I can, in my window, if I change my scale on the y-axis to actually count by 25s, just like it does on the paper. All right, wow, it looks even more like it. Yeah, that looks awesome. Okay, so you can see that every little count here is 25 and on the bottom it's ones. And so it definitely looks very, very similar. How did we arrive at that conclusion? Well, we made the windows match, and so then the graphs do in fact look the same, okay? So there's really nothing to write down for number 3. It was just matching it up in your calculator. Okay, so let's move on to number 4, which says divide the region under the graph from t equals 0 to t equals 8, which represents the distance, into 4 vertical strips of equal width. Okay, so I want to do equal width along the bottom. So let me erase some of this other stuff I was drawing. Equal width along the bottom from 0 to 8 into 4 strips. Well, I hope that's not too hard for you. We're going to count by 2s so that we can divide it up at 2, 4, 6, and 8. So let me get. All right, so I'm just going to draw. It's hard to do a nice straight line with my little writing tool, but we'll figure it out here. All right, so we've got 4 vertical strips. We've got one going from 0 to 2, another one from 2 to 4, 4 to 6, and 6 to 8, okay? And now it goes on to say draw 4 trapezoids whose area approximate the areas of these strips, and then whose parallel sides extend from the x-axis to the graph, which is what we just did, okay? So I drew these lines from the x-axis to the graph, so they touch the graph, all right? And I want to turn these strips into trapezoids, okay? And so I'm going to connect my points, basically, with a diagonal line, all right? Or in some cases, we might have to go straight across, all right? But we're making trapezoids. So these are not supposed to be tracing the curves exactly. They are supposed to be, straight. The best you can on your paper, okay? All right, so there are my trapezoids. And then it says, by finding the areas of these trapezoids, let's estimate the distance Ella goes and see if our answer agrees with what we got back in problem number 2. Okay, so recap, how do you find the area of a trapezoid? All right, area of a trapezoid is 1/2 base 1 plus base 2 times the height, or in our case, that's going to be our width along the bottom. Okay, so base 1 and base 2 are actually our sides of our trapezoids, and the height is actually on the bottom. Okay, and so let's see, we're going to do half. And then base 1 is going to come from the velocity at time 0. And base 2 is going to come from the velocity at time 2. And then I'm going to multiply that by a width of 2. Okay, that's just the first trapezoid. Then I'm going to do it again. Half. And then the second trapezoid has a side that's representative of velocity at time 2. And the other side is at time 4. And that one is also 2 wide. And then I'm going to do it again for the third and the fourth. Okay, so the third one has a side at V of 4, and the other side is on 6, and it is 2 wide. And then the last one goes from 6 to 8, so V of 6 plus V of 8. These are Y values, right? How tall they are times the width, okay? Now, I can actually do some quick simplifying here because 1/2 times 2 in every single one of these cancels. So that would give us a lot less to worry about typing in. And then I want to come up with my values here. Well, I know that we're estimating from the graph, but because we have the function typed into our calculator, we're going to actually use our calculator to find these values. Okay, now I do want to show you that look what you're adding up. You do have a couple of the same things. So you've got a velocity of 0, but then you've got 2 V of 2s and 2 V of 4s and 2 V of 6s and then 1 V of 8. Okay, so I can even shorthand it a little bit more, just so canceling out the 1/2 and the 2s and then combining like terms. And now I'm going to pull up my calculator to do the work here. Okay, now let me pull it up. All right, now remember where your velocity function is. It's in Y1. All right, so I'm going to go to a blank screen and I'm going to literally make the calculator bring up Y1. So I'm going to hit alpha trace, choose Y1, and I'm going to do of 0. Right, so that's my velocity of 0, V of 0. Okay. And then I'm going to do, see if I can slide it over here. There we go. That's almost enough. Okay. Then I'm going to do plus 2 times V of 2, but that's in our calculator, that's Y1 of 2 plus 2 times Y1 of 4 plus 2 times Y1 of 6 plus Y1 of 8. Enter. Okay, and so I get 1,472 miles. Okay, and then does that somewhat agree with what we estimated? Well, our estimate was a little higher, but they're somewhat close. Okay, now number 5 says, do you think the trapezoidal sum from problem 4 overestimates or underestimates the actual distance Ella travels? And we're going to come up with a formal explanation of how we know. Okay, so if you look at the picture, you can kind of see you've got a little bit of space that's not accounted for when you draw your trapezoids. Okay, so it is definitely an underestimate. Okay, so underestimate, but why? I need a specific reason. Okay, and when you're using trapezoids, underestimates and overestimates are based on concavity. Okay, so it's an underestimate because V of t is concave down. Right, so put that somewhere where you can look over it again later. All right, trapezoids underestimate concave down curves. Trapezoids overestimate concave up curves. Because notice, it doesn't matter if it's increasing or decreasing, because this graph is doing both, okay? It's all about the concavity when you're talking about trapezoids. So again, make yourself a note somewhere other than here that trapezoids underestimate concave down curves and overestimate concave up curves. Okay? Well, in our lesson today, we talked about these things called Riemann sums, which was adding up a bunch of rectangles. Okay? Well, a trapezoidal sum is sort of a Riemann sum, where you're literally adding up, okay, that's this mathematical symbol, the sum of some sort of function evaluated at individual places. So in our case, v of 0, v of 2, v of 4, v of 6, right, times a width, okay? So you're taking basically, and your function is the average height, that's the trapezoid part, okay, times the width. And then the exact value, so this is where we're kind of pulling it all together, the exact value of the definite integral, okay, would literally just be the limit of the estimate by trapezoids. Meaning the more trapezoids we use, the closer and closer we get to the exact value. And so if we take the limit as the number of trapezoids goes to infinity, or the width goes to 0, depending on which way you want to think of it. So the width of the trapezoid is so infinitely thin you can't actually measure it. That's when you get an integral, a definite integral, okay? So in number 6 here, the exercise actually says to double the number of trapezoids to 8 and estimate the distance Ella travels. Okay, so I will certainly leave that to you. I do encourage you to practice it. So you're going to break it up into 8 equal subintervals. They're all going to have width of 1. And then it goes on to say, does your answer agree with the answer to problem 2? All right, and do you think the trapezoidal sum still underestimates the actual distance? Well, it definitely should, because it's still a concave down curve. All right, so I will tell you, all right, and I absolutely encourage you to go back and do this on your own, that when you work this out for good practice, all right, you should come out with 1,508 miles for the answer to that approximation, but it is definitely still an underestimate because it's still a concave down curve, okay? All right, and then it just goes on to talk a little bit more about the definite integral. So it says when a function rule is given, like our v of t, graphing calculators have a built-in operation to evaluate, right, which is literally just very accurately estimate a definite integral. Okay, so what we're going to do is we're going to use our graphing calculator to integrate to evaluate the integral from 0 to 8 of v of t. All right, so on my calculator, let me pull it back up. All right, we talked about this a little bit. If I want to, the integral symbol, I have to hit math 9. We're going to put 0 at the bottom and 8 at the top. All right, now you can either type your v of t function in again, or you can tell it that you can tell the calculator that it's already in y1. So I'm going to hit alpha trace and choose y1. And then you do have to tell it that the variable is x, so dx. We're going to hit enter. All right, and look at that, 1,520, and it, I don't know how we got so lucky with our first approximation. We got pretty darn lucky. I guess I did a really good approximating by saying 60.8 squares, all right. And so do you think the trapezoid sums still underestimate the actual distance? Well, yeah, because the two values that we found back in question 4 and 6 were both less than 1,520, so they're still underestimates. But the more trapezoids we use, the closer and closer we're going to get to that 1,520. Okay? All right. Well, now let's do some rate of change review, okay, and bring all that together. So it says, what is the fastest Ella went? Okay? The fastest Ella went. And then show how you arrived at your answer and what time was that. Okay, so let's talk about how do we find the fastest. Okay, well, Ella went the fastest, hopefully you're thinking about this, when, right? So that's when her acceleration, I guess, well, no, that would be like her speed. So it's really when her velocity has a max, right? She's going to go the fastest when her velocity has a max, all right? Because, I mean, if she's actually, yeah, I don't want to misexplain something. So we're going to say Ella went the fastest when velocity has a max, all right? And so because I actually have my v of t function in my calculator, I need to literally find the max on the graph. Okay, so we're not approximating this because we actually have a function. All right, so we have to remember how to find a max on a graph. We're going to hit second, trace, and we're going to choose number 4, maximum. And remember, you have to move your blinker, your little cursor, all right, so close to the top, but pay attention to your y values, all right? You don't want to do the absolute biggest, so we are, all right? All right, so we're just kind of watching the y values to see where it's roughly the biggest, and then do a little bit to the left of that, then go back and go, wait till it starts going down again, that's the right, and then take your guess somewhere in the middle, okay? And then it will calculate the maximum for you. All right, and so what is the fastest Ella went? Okay, that's the actual y value. All right, at what time was that? That's the x value. Okay, so Ella went the fastest when v of t has a max, and that happens at time, all right, t equals, let me pull my calculator back up, 3.042, we can round that, at time equals 3.042 minutes, all right? And, but she was going, because the question is, what is the fastest? Ella was going, right? And that's where we're going to look at the y value, 248.021. 248.021 miles per minute. All right, that was the fastest. 248.021 miles per minute, and it happened at time t equals 3.042. Okay, and show how you arrived at your answer. I literally found when v of t had a max, and as long as I write that down, I can do that with my calculator. Okay. All right, number 9 says approximately what was Ella's rate of change of velocity? Rate of change of velocity means derivative of velocity at time 5, which is the same thing as acceleration at time 5. Well, how do I do that? I use my calculator. I have an actual function in my calculator, okay? And the function in my calculator is v of t. Whoops. All right, so if the function is v of t, I'm going to let my calculator take the derivative of that function. So I'm going to do math 8. Nope, not there. Sorry, I need to get out of that screen. Then I can do math 8 and take the derivative with respect to x of the function in y1 at time 5. Whoop. Time 5. All right, and so that came out to be negative 34.9 repeating. Well, when you round to 3 decimal places, you are going to have to round up to negative 35.0, and that's acceleration, so that would be miles per minute squared, okay? And then I want to know, was she speeding up or slowing down at this time, and how do you know? Okay, so that's another review. Right? How do I know if something is speeding up or slowing down at a specific time? Well, I need the acceleration at that time and the velocity at that time. So my calculator, how do I just find the velocity at time 5? Well, then I literally just need to plug 5 into y1, right? And that is 210, and that would be miles per minute if we're keeping up with our units. All right, so her acceleration is negative 35 miles per minute squared, and her velocity is 210 miles per minute. Well, remember, you're comparing the signs, right? So we've got a negative and a positive, all right, which means Ella is slowing down. All right, so this goes back to something that we've talked about pretty good. I mean, it's been a while, okay? So just, again, trying to always throw in some review. So Ella is slowing down at t equals 5 because, how do we know? Because a of 5, acceleration at time 5, and velocity at time 5 have different signs. Remember, if they had the same sign, she would be speeding up. Okay, so hopefully you remember that. All right, and then the last little question here says, based on the equation in problem 3, there are positive values of t at which Ella is stopped. What is the first such time? How did you find your answer? So we're literally using the v of t equation, not the starting graph. It says, based on that equation, there are positive values of t at which Ella is stopped. Okay? What is the first such time, and how did you find your answer? Okay? So if she stopped, right, she's not going anywhere, she's not moving in any direction, all right, then we know Ella is stopped when, right, hopefully you're thinking for yourself, when velocity equals 0, okay? Ella is stopped when velocity equals 0, all right? Now, how do I find such time? What is the first such time? How do I find it? Okay, well, I'm going to go to my calculator, since this function is in my calculator, and I'm going to look at the graph, and I want to find when is it equal to 0. Now, I might want to change my window, all right, because it looks like it happens down here in the corner. So let's go down a little bit more sorry, I don't need to do, that one can stay 0. Let's go a little bit further out in the x direction, maybe to 13, just to be safe. Hopefully, it looked like it happened right there at the corner, but we'll go a little bit extra. And then, of course, for the y minimum, just to make sure that we can go below and above, I don't know, let's make it negative 10 or 5, okay? And go back to our graph. All right, so it just gives us a little bit more to look at, and we can definitely see that it becomes 0 in here. You could even zoom in on that space by moving your cursor much closer to that section of the calculator, and then hit enter, and it'll zoom in on that specific spot. All right, and then you can do second trace and actually calculate a 0. Okay, so we need to give it a left bound. Ooh, look, there's some, look at your y values. You definitely do have some, and we want the first time it becomes 0. So be careful on that. All right, so we've got some positive y values, and they're getting smaller and smaller, and now they're negative. Okay, so for the left bound, you want something that would actually be positive, and the right bound, you would want something that's negative, and then you want to take your guess in the middle. Okay, and you do want that first time that it happens, and it looks like it's at 10.916. Interesting. It's not what I have on my paper, but that's okay. So I must have found a different time. All right, so this happens at t equals, what did we say, 10 point, where's my calculator go? 10.916 minutes, right? 10.916 minutes. Okay, and how did we find their answer? We literally, and we kind of already wrote it, we found when v of t equals 0. Okay? All right, so that concludes our video on more definite integrals. I apologize that it's 30 minutes, but I do hope that you take the time to watch this and practice some of this on your own.